There's a life vest under your seat. Not a parachute, a life vest. On a plane that spends almost its entire flight over land. You've probably buckled in, half listened to the safety demonstration, and never once stopped to ask why. But that question, once you actually ask it, pulls on a thread that unravels almost everything you thought you understood about what keeps you alive at 35,000 feet. Here's what nobody tells you in the boarding announcement. The reason there are no parachutes on a commercial airliner isn't negligence. It isn't cost-cutting. It isn't some dark corporate calculation about liability versus passenger comfort. It's physics. Pure, brutal, unforgiving physics. And once you understand it, you'll never look at a cabin the same way again. Start with where you are when the problem would actually matter. A Boeing 737 at cruise altitude is traveling at roughly 570 miles per hour. It is 8 miles above the ground. The outside air temperature is around -60 degrees Fahrenheit. The air pressure up there is so thin that an unprotected human being loses consciousness in about 12 seconds. Not 12 minutes, 12 seconds. That is the environment in which someone is supposed to open a door, step out, and pull a cord. Here's what actually happens the moment that door opens at cruise speed. The pressure difference between the cabin and the outside atmosphere is enormous. The door wouldn't swing open gently. It would be blasted off its frame. Anyone near it wouldn't jump. They would be pulled out instantly, tumbling into an airstream moving faster than most military jet aircraft fly in combat. The wind blast at 570 miles per hour doesn't feel like wind. It hits the human body the way a concrete wall hits a car in a head-on collision. At that speed, the aerodynamic force on an unprotected person is enough to strip away clothing, cause immediate loss of consciousness, and produce injuries that are unsurvivable before the parachute ever has a chance to open. The parachute was never the problem. Getting to the parachute was always impossible. But let's say you solve that. Let's say someone engineers a pressurized ejection capsule, a military-style seat that fires a passenger clear of the aircraft before they're exposed to the raw airstream. Fighter pilots have them. The technology exists. Why not build that into a commercial cabin? Here is where the numbers become a wall you cannot reason your way around. A modern military ejection seat weighs roughly 250 pounds. It contains explosive charges, a rocket motor, a drogue chute, a main chute, an oxygen supply, and a full survival kit. It costs somewhere between $400,000 and $1 million per seat to manufacture and maintain. It requires specialized training to use correctly under extreme stress. And it carries a real injury rate, even when it works exactly as designed. Spinal compression fractures from ejection are common enough that militaries track them as a standard occupational hazard among pilots. Now put that seat on every row of a Boeing 747. A fully loaded 747 carries up to 416 passengers. 416 ejection seats, each weighing 250 pounds. Before you add a single passenger, a single carry-on bag, or a single gallon of fuel, would add over 52 tons of hardware to an aircraft whose entire operational logic is built around precise, obsessive weight calculations. That is the equivalent of loading 40 full-size pickup trucks onto the plane before it even taxis to the runway. The aircraft couldn't take off. And that's before you address the roof. Ejection seats fire upward through a canopy. A commercial aircraft has rows packed tightly across a wide fuselage, passengers on both sides of the aisle, overhead bins running the full length of the cabin above their heads. There is no clean ejection path. The seat in row 32 on the left would fire directly into the seat in row 32 on the right. The seat in the window position would fire through the fuselage wall rather than through any opening. The geometry alone makes it mechanically impossible. Not impractical, impossible. And none of this touches the question of sequence. If 400 people attempted to eject from a stricken aircraft, who goes first? How do you ensure the person in the window seat doesn't get killed by the ejection blast of the person in the middle seat firing a split second earlier. Military aircraft with 2 seats have choreographed ejection sequences that take years to engineer for just 2 people. 400 people in a metal tube at altitude is not a problem with a sequence. It's a catastrophe with extra steps. Here's the moment where common sense tells you one thing, and the actual data tells you something completely different. The instinct behind the parachute question is completely understandable. It says, things go wrong, and people should have a way out. It feels like an obvious gap in the design. It feels like the kind of thing a safety engineer should have caught decades ago and fixed. The question feels responsible. It feels careful. But here is what the data says. Commercial aviation's fatal accident rate is approximately 0.07 deaths per 1 billion passenger miles flown. Put that in terms a person can actually feel. If you boarded a commercial flight every single day for the rest of your life, your statistical odds of dying in a crash are roughly 1 in 11,000. You are meaningfully more likely to die on the drive to the airport than on the flight itself. In most years in the United States, more people die falling out of bed than die in commercial airline accidents. That is not a figure designed to be reassuring. That is just what the numbers say when you look at them honestly. The parachute question assumes the underlying system is fragile and in need of individual escape routes. It isn't. The system is already so extraordinarily reliable that layering an individual escape mechanism on top of it doesn't make passengers safer. It makes the aircraft heavier, mechanically more complex, significantly harder to maintain, and by introducing new failure points and new variables, statistically more dangerous to operate day after day. The solution to surviving a commercial aircraft accident was never going to be a mechanism for individuals to bail out mid-flight. It was going to be engineering the aircraft so thoroughly, so relentlessly, so obsessively, that the scenario requiring individual escape almost never happens. So that's exactly what the engineers built. A Boeing 777 does not have one hydraulic system. It has 3, each completely independent of the others, any single one of which can fly the aircraft alone if the other 2 fail simultaneously and completely. It has 2 engines and is certified to fly over open ocean for up to 330 minutes on a single engine alone. Its fly-by-wire flight computers run multiple redundant processors that cross-check each other's outputs thousands of times every second. If one processor produces an anomalous result, the others outvote it before any control surface has moved a single degree. The landing gear has a gravity-free fall deployment backup that drops the wheels into position using nothing but gravity and a mechanical latch release. No hydraulics, no electrical signal, no crew command required. The aircraft's flight data recorders are mounted in the rear section of the fuselage, the most structurally survivable location in any impact scenario, and are built to withstand a force of 3,400 times the force of gravity and direct fire at 2,000 degrees Fahrenheit for a full hour. Every one of those systems is a parachute, not for one person, for everyone on board. Each redundant pump, each backup computer, each fail-safe circuit that will never trigger in 1,000 flights because nothing will go wrong. That layered obsessive redundancy is the engineering equivalent of giving every single passenger a personal escape route. Not out of the aircraft and into the void at 8 miles altitude, into a machine so deeply over-engineered that it is specifically designed to keep flying, even when significant portions of it have already stopped working. This is not theoretical. There are documented cases of commercial aircraft landing safely after losing both engines simultaneously, after losing all hydraulic pressure and flying with control inputs fed through differential engine thrust alone. After structural failures that tore open the fuselage mid-flight and exposed passengers to open sky, the aircraft kept flying because the redundancy ran so many layers deep that there was always one more functioning system beneath the system that had just failed. No individual parachute replicates that outcome. a parachute gets one person to the ground in an open field somewhere. Redundant engineering keeps 400 people inside a functioning aircraft that touches down on a runway, with the crash trucks already rolling into position. There is one genuine exception worth understanding, because it proves the rule rather than breaking it. Small general aviation aircraft, the single-engine planes carrying 2 to 4 passengers that you see at regional airports, operate in a completely different physical world. They fly lower, slower, and without the crew depth or systems redundancy of a commercial jet. A company called Cirrus Aircraft actually integrated a whole aircraft parachute system into their SR series planes. Not individual chutes for the people inside, but a rocket-deployed ballistic canopy that lowers the entire aircraft to the ground as a single unit. It is deployed in real emergencies. It has saved real lives. It works because the aircraft weighs under 4,000 pounds and flies at under 200 miles per hour. The physics allow it. The canopy is manageable. The deployment forces are survivable. The geometry cooperates. Now scale that up. A fully loaded Boeing 747 at cruise weight tips the scales at around 900,000 pounds. A parachute canopy capable of slowing that mass to a survivable descent rate would need to be roughly the size of several football fields laid side by side. The deployment shock, the instant the canopy catches air and the load transfers, would generate forces large enough to structurally destroy the aircraft before it had descended a single foot. The solution tears apart the thing it was supposed to save. The physics don't cooperate at that scale. They never will. So the next time you settle into your seat, clip your seatbelt, and half listen to the flight attendant explain the brace position and the exits, here is what's worth holding on to. The life vest under your seat is there for water landings. That's a real scenario, rare but real, and the vest is the right tool for it. The reason there is no parachute under that same seat isn't that nobody thought of it, isn't that the airline calculated it was cheaper to leave it out, and isn't that regulators failed to demand it. It's that the engineers who designed the aircraft you're sitting inside already solved the survival problem. They solved it in the airframe. They solved it in the hydraulics. They solved it in the computers cross-checking themselves behind panels you'll never see. They solved it so completely and so quietly that the question of what happens if this fails almost never has a real answer to give, because the failure almost never comes. You are already wearing the parachute. It just weighs 900,000 pounds and has redundant everything. Now here's something almost no passenger ever thinks about. If the aircraft is engineered so obsessively to survive, what happens to the landing gear during a crash where everything else has already failed? The wheels on a Boeing 777 are not designed to hold on. They are specifically designed to shear away cleanly in a precisely controlled direction so that the gear legs do not punch upward into the fuel tanks mounted in the wings directly above them. The landing gear is built to fail on purpose. The failure mode is engineered as carefully as every system designed to succeed, and the physics behind that decision are just as precise, just as deliberate, and just as counterintuitive as anything else hiding inside that aircraft. If that's the kind of engineering that makes you look twice at the machines carrying you through the world every day,